So today we're going to be talking about the basic statistical measurements. This is review for sure because you've calculated the standard deviation and the average of a set of data before. I mean, how could you not, right? But we will talk about pooled standard deviation today. So maybe that's new. I don't know if you've used that. Did y'all get into that in quant, pooled standard deviation? It's probably because you didn't compare or collect all the different groups of data. So this is what you have. You have group 1 and group 2 and group 3, each producing different means and different standard deviations. How do you get an uncertainty for the whole group? So you have to use this pooled standard deviation. And that's important too. If you have different analysts and they have different sets of runs and so on, and you want to see what the standard deviation is for the whole lab, then you would use the pooled standard deviation. So we'll introduce that today. So let's begin at the beginning. So this is the part of the course about quality control. And honestly, it's about trust. People have to trust your data. You have to have trust in your own data. So you should want to do this anyway just to see how well you're doing, right? When you measure something, what's your uncertainty like? And compare that to the mean. That's what we talk about, the relative standard deviation. You have a standard deviation and then you have your measurement. What is your uncertainty relative to your measurement? It's another way of thinking what's your signal to noise, only this time the noise is on top. It's your noise to signal. And so if your relative standard deviation is 50%, that means 50% of your signal is noise. And that's not good. Okay. So your expert testimony is going to be based upon scientific facts and data, of course, but also reliable principles and methods. And then those methods applied reliably to the facts of the case. And so the quality assurance defines what we mean by reliability. And without statistics, you can't have reliable measurements. So we've got to make sure we understand how to apply statistics to our measurement systems. So this is all of the weight of the forensic lab resting on your shoulders. So this triangle is pointed right at you, down at the bottom. So up at the top, you have like national accreditation agencies, and in the middle, you have professional agencies, accreditation, like you're certified technician in this area, say for drug analysis and so on. And then that third triangle that's lower is the one that's within your lab. So quality assurance procedures, training requirements, and so on. At Pentex, we had, this is the company that I worked for before taking this job, we had quality cards that we wore. We had a name badge, and then behind that we had a qual card. And it said when you were trained on that instrument and when that training expired. And so someone from like an agency could come in and check, and they see you running the FDIR, and they come up and say, let me see your qual card. Are you trained on this instrument, and when do you need a refresher on that? And so you can show them your qual card, and if you were outside, if your training had expired, they would ding the company. And so that was pretty stringent, okay, but you know, again, that may exist in some professional forensic labs where you have qualifications with expiration dates. And then down at the bottom, you have the analysis and controls and control charting and things of that sort that you implement so that you can have trust in your own data. And then if you trust your data, then you can convey that trust to others. So let's begin at the most simple thing. Let's review significant figures. So this goes back to middle school probably, but certainly freshman Chem 1, where we talk about reporting data. And the reason I start here is because this is the convention that you use, the significant figure convention, if you don't know your uncertainty. And so at the freshman level, we have one measurement, we have one number given, we don't give them plus or minus anything, that would freak them out. Okay, so how do they estimate the uncertainty if they're just given a number? Okay, we have to use this. This is the last resort for guessing, essentially guessing at someone's uncertainty. And so it's the leading zeros are not significant. They have no meaning to this precision of the data. So if you have this number, where's the uncertainty lie? It lies in that last digit. So the overarching principle is we keep all the certain digits and one uncertain digit. And we call those significant figures. If you have decimal place, then trailing zeros are significant. So 1.200, you're saying something about the precision by including those last two zeros, and you've shown them because you've given that decimal place. Captive zeros are significant. So if the zero is between two non-zero numbers, then it's significant. And then you never append zeros without justification. So just to make the math work out, don't append those zeros. If you do to make the math work out, know that you're going to have to remove them later. You know, that you're not adding certainty just by adding zeros. And then we have multiplication and division, and those are treated separately than addition and subtraction. So that's a principle. So if you're drowsy this morning, right now, wake up and think, okay, addition and subtraction are in one category, multiplication and division are in a different category, both for significant figures and for propagation of uncertainty. So in both cases, we treat those differently. So whenever you're doing a mathematical operation, you need to know, am I doing an addition or subtraction? I treat the uncertainty one way. If I'm doing multiplication and division, I treat the uncertainty a different way. So in this case, multiplication and division, we retain the least number of significant figures. So if I have 11 times 0.05, I only have one significant figure, that 0.05, the 5 in that 0.05. And so then I round the result, okay? You might think it's 0.55, but we would round that result up to 0.6. Okay. Subtraction and addition retain the least number of decimal places. So notice now we're dealing with decimal places. If you're using scientific notation, that's a problem. So you've got to figure out what the powers of 10 are and get them all. Well, that's good. I have no malware. If we're doing multiplication or doing subtraction and addition with scientific notation, we have to get everything in the same power of 10. Because the powers of 10 are what decide what the place value are. Okay? And so there's some practice problems on the little practice exam that you can do that test you on that. But that's probably the number one problem that people miss on that practice exam that shouldn't be missed. It's significant figures. How hard can it be, right? But when you add in scientific notation, you've got to figure out that 10 to the 5 and 10 to the 3 matter. Okay, so you got to get everything into the same power of 10 before you can do the addition and subtraction and keep track of your decimal places. So these are the rules for the significant figure convention. And just think about it too logically. You know, if I tell you I have $1,100, okay, and I'm not putting a decimal place on that, I'm telling you my uncertainty is in the hundreds. Okay, if I write it down 1,100 and no decimal place, the uncertainty is in the hundreds place. But if I put a decimal place, then I'm saying that I counted it out to the ones, and I have exactly $1,100. Okay, you follow me? So that decimal place is important for trailing zeros. Let's look at some of the statistical terms. Okay, so the significant figures, they will tell us where to round. Let me do one or two examples. We've got the addition and subtraction and the multiplication example here. This is the one that freaks people out. So I don't have to do this on the board. Look at that. 11 minus 0.05 is 11. I see you nodding, so you're like, okay, I agree with that. But it is weird, right? And so, you know, if you're uncertain in the ones place, you really have no idea about the hundredths. And so that's what we're talking about. We're talking about certainty. And where's your uncertainty? If I look at this number, these are called place value. This is the ones place value, and this is the tens place value. And I'm telling you I'm uncertain in the ones place value. Okay? And here, I'm telling you I'm uncertain in the hundredths place value. And just by doing a subtraction, I don't all of a sudden gain precision. All right? I can't have the result be certain in the hundredths if one of my numbers is uncertain in the ones. And so I'm telling you, I don't know if it's plus or minus $1. Don't ask me about nickels. Right? So it's where that place value is in terms of uncertainty for addition and subtraction. Okay. So let's look at the statistical terms. This is some review as well. So we have a sample, and a sample is a small number of observations, and by sort of convention, we say less than 15. Okay. And a population, of course, so the symbols for a sample would be X bar or X in angle brackets. So whenever you see me write X bar or X in the angle bracket, I'm talking about the mean. Okay. Or if you put angle brackets or bar on anything, like if I'm measuring density and I put density bar, that would be the average density, or density in angle brackets, that's the average density. Okay. And then a population would be an infinite number of observations, or 15 or more. So you didn't know that 15 was infinity, but it is. Okay. So the mean symbol is mu, Greek character mu. And so if you write that, you might write mu with a subscript, like the mu density. That would be the average density written for a population. If you had a large number of measurements of density, and you could write mu with a subscript density, or r, or rho. And then we have the standard deviations. The standard deviation for a sample is S. The standard deviation for a population is sigma. I will use the word sigma a lot to indicate standard deviation. Even if I'm talking about a sample, I'll just use sigma to talk about standard deviation. But the real symbol that we use is S, not sigma for a sample. There's only one significant difference between the two, and that is for the sample population, we use the n-1 in the denominator. So looking at these two equations, which one of those is larger? They have the same data. They have each x measurement. This is individual measurements, and this is the average of those measurements. And so think about the term too. What is this called? The standard deviation. Let's break that apart. What does deviation mean? Yeah, so here you got the mean, and now how do your sample, your individual measurements deviate from that mean? Okay, and so that's why we're calculating the differences. Now, if I was to try to take the average of those differences, some are going to be positive, some are going to be negative. And so when I add up all of those, the negatives are going to cancel the positives. And so no one likes that. So we're going to square them to make them positive. So even the negative ones become positive when we square them. So we take each individual deviation from the mean and we square it and add them together. Okay? And so now we have the sum of all of these deviations squared. And then it's kind of like taking the average. If we have 7 measurements, we have 7 deviations squared, we've added them together, we divide by 7. So we're taking the average deviation. Only because it's the deviation squared, we don't call it the average, we call it standard. It's just the standard deviation. And since we've squared it, we're now in sort of a different range of values. And so we unsquare it. We take the square root. So we square those deviations, we add them together, divide by the number of measurements, and then we unsquare them. And then we have the standard deviation. So that's that equation explained to you. And that's what I'd like for you to be able to do, look at any equation and read it like a paragraph. So this is the standard deviation equation, but for a small number of samples, we might be pretty far off. You know, you only measure it 3 times, you may be off. Maybe, each of those 3 measurements were high and you didn't know it. And so we'd like to have a larger estimate of our uncertainty. We'd like to be more conservative. Like if I'm telling you my results and the mean is this and the uncertainty is this, I don't want to be wrong. And so I want to tell you maybe a little bit bigger uncertainty, just to be safe. If I want you to trust my results, I'm going to say, look, I'm giving you the worst case. And so for a sample, we subtract 1 from the number of measurements, and that's actually called the degrees of freedom. The variability in the data has a lower number of degrees of freedom because we've used up 1 degree of freedom in calculating the mean. And each one of these has the mean in it. So we've used up a degree of variability by calculating the mean. And for the sample, that's significant. For the population, it's not significant. And we can see in the next slide the chart of the two. So here's the sample and the population data in the red and the green. So as the number of measurements increases in this particular set of data, notice how the standard deviations converge. They don't become exactly the same, but they're close enough to the same at around 14 or 15. Is there something magic that happens at 14? No. Okay, so like I said, it's just convention that we say 14 or more, 15 or more data points, you have a population. Okay. I'm going to turn off that middle light. That better? Now, we have a mean and we have a standard deviation, and so these two figures of merit, think about that term, figure of merit. It's a number, figure is a number. Merit is how good something is. And so there's two, in that gray box up there, 2 very important figures of merit. So how good is your data set? The relative standard deviation is very useful. That RSD is the standard deviation over the mean. That must be part of you. Like you must have that so internalized that you can go from RSD to mean and standard deviation and back and forth. That is a skill that you shouldn't even have to think about. Okay, so if I tell you the mean is this and the relative standard deviation is that, you don't know sigma because it's buried inside the RSD. So you should be able to figure out, I just got to multiply that RSD by my mean and I get my sigma. Okay, so it's just a simple equation. It's RSD equals S over X bar, and you should be able to get to X bar or S. Given any two, you should get the third. Just no problem. Okay, now the RSD, again, is going to be, it's a unitless number because the units of S and the units of X are the same, so it's a unitless quantity. And sometimes we like to express it in percent. And so we just multiply by 100%, and that gives us the coefficient of variation. That's a fancy word, coefficient of variation. And it's just your RSD times 100%. Now, what if you're really good? You've got a fantastic instrument, and it has very low noise, and your RSD is like 0.0003. I mean, it's like 0.3%. You may want to represent it in parts per thousand, so it'll be 3 parts per thousand. So instead of percent, you might multiply by 1,000 parts per thousand. Or if it's really good, like insanely good, you might be reporting it in parts per million. So if it's 0.000045, you multiply that by 10 to the 6 parts per million. Okay, and so then you've moved the decimal place 6 places over there, and now you have what it's like 45 parts per million is your CV. Okay, so it's just how to report small numbers. Now, did you notice that if it's 100 parts per 100, that's percent. So you're multiplying by 10 to the 2%, 100%. But if it's parts per thousand, what is 1,000? 3 zeros. So 10 to the 3rd parts per thousand. Million, 10 to the 6th parts per million. And billion, 10 to the 9th parts per billion. And in a ridiculously improbable case, 10 to the 9 parts per trillion. Okay. Also, if you have multiple measurements, your standard deviations with different groups, here's the pooled standard deviation. So let's see if we can understand this equation. It looks, somewhat complicated. You have the standard deviation for group 1 here, and it's squared, and the standard deviation for group 2, and it's squared. You have the number of measurements for group 1 minus 1. So what is that? That's the degrees of freedom for group 1. And this is the degrees of freedom for group 2. And down here you have all of these added together, minus 2. So you have 2 groups here, minus 2. So this is the sum of all the degrees of freedom in all the different groups. And this is just a weighted average. If you look at it, it's the degrees of freedom for group 1 times their variance. And that's a new term. That's standard deviation squared is the variance. And so you have the degrees of freedom of group 1 times their variance, and the degrees of freedom of group 2 times their variance, divided by the total degrees of freedom in the whole room. Since we're dealing with variances and we want the standard deviation, we take the square root and we get the standard deviation for the whole room. We'll actually do this in a second. Now, let's talk a little bit about analog versus digital measurements. Sometimes analog is better. Right, you're looking at the needle, and it's right there between the 2 marks, 125 and 126. It's acceptable to estimate 1 digit beyond the tick marks. This could be a burette. This could be, a voltmeter. It could be anything that has tick marks, and you're measuring it with your eye. You can estimate 1 digit beyond the tick marks. So in this case, our tick marks are in the ones place. So our uncertain digit is in the tenths. Doesn't that match what we defined? Keep all your certain digits and 1 uncertain digit. That's the measurement principle. And that's what you would report. Are you certain it's greater than 125 over here? Yeah, the needle is definitely past 125. It's definitely below 126. So I'm going to write down 125. I'm certain of that, but I'm uncertain about whether it's 0.5 or 0.6 or 0.4. So that's my uncertain digit. So I would estimate on this case, 125, I could say 0.4 or 0.5. You know, it's probably not 0.1 if you look at the location of the needle. Okay, so I give my best estimate for where that needle is. If it was about a third of the way, I would say 125.3, you know. And so that would be my estimate. And so I would have 4 significant digits in that measurement. On the balance, occasionally you have this situation. Everybody have this on the analytical balances? And you're like, okay, it won't settle down. But if you start to see a pattern, oh, it's going down and up, down and up, down and up. Most of the time it's just dropping. Okay, I don't know why that happens, but it does. You know, but if it's doing this, then you can estimate 125.4, 125.5. You know, you could probably say 125.45. You're certain it's 0.4 because it's never gone below that. And again, you're going to make multiple measurements and it'll all straighten out. But if you were trying to be as precise as possible, you could say 125.45. Is it 0.44? Who knows? You're uncertain. And that's what uncertainty is. But you're not totally clueless. You're not going to say 125.8 or anything like that. So anyway, this is just, again, how to read different meters, different burettes, and so on. Pay attention to the tick marks because the company that made that measurement device is telling you, you know, how precise it is and what kind of behavior you should have. This is all part of a measurement system evaluation. You know, the balance will tell you what the uncertainty is and the repeatability of that balance. If you look at the box that you get for like a 4-place analytical balance, it will say it measures to repeatability to 0.0002. So it's really 2 plus or minus 2 in that last digit, not just 1. That's what the company will tell you. But your particular environment may not allow that balance to operate to its fullest extent. You know, if you put it on one of these lab tables, like if I put the 4-place balance here, you really see it with a 5-place balance, right here in the middle of this table, this is like a drum head, and sound will make it vibrate. And you're trying to measure something on a balance, and the bottom is vibrating, and the computer's trying to figure out what the mass is. It oscillates all over the place, and then somebody comes along, boom, 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 and you know it's resonating with the stereo outside or the diesel truck, and your measurements are off. Okay, so anywhere you're looking at a table, right here is where I would put the balance. What did I look at? What do you think I looked at? No, there's a wall underneath the table right here. So this is going to be a node. This table is going to vibrate no matter what, but I'm sitting right here on top of a wall on this table. So just moving that balance a foot can improve your uncertainty. And it's just worthy of taking an account of where you place your measurement devices. And so verification and control charting should be done. We could verify this balance position with the weights and so on. You could put a 1 gram weight, a 1/10 of a gram weight on there and measure the high end to 100 gram, a 200 gram. Work against these primary standards. You can buy these weight kits that are NIST traceable. They're brass or even like in some cases gold coated so that it doesn't grow mass by reacting with oxygen. You never touch them with your hands at all. You use tweezers or gloves, and it's really important for the tiny masses. I mean, you could probably touch the 1 kilogram mass, but still. But mass is typically the foundation of measurement, and we calibrate our volumetric equipment with the mass. So have you done that to the pipettes, and you measure the pipette repeatability and so on. So it all starts with calibrated balances. And so then we just build this pyramid from mass through volume to all the different measurements that we have. And so each step is always affecting the others, and that's why we need to do propagation of uncertainty. So before we get into propagation of uncertainty, let's do a measurement exercise. So I will pass these out. And the way this works is I will give different instructions to different groups of 5 people. Okay? And follow those instructions. You all have the same circle to the best of my ability of cutting these out. Who's talking? No,
Me.
Okay. Okay, so let me have, let's see, you three on this row and you two. Okay? You guys can't talk to each other. Sorry. Okay, so y'all can't talk to each other. You'll just manage yours. So the instructions. Okay, let me tell everybody what we're gonna do is I'm gonna pass these circles out, and I want you to measure the circle. Okay, so that's the exercise. That's all the instruction I'm giving you is measure the circle. Okay. Just measure it one time. Okay, now you two can talk to each other. Okay. Talk softly so this group doesn't hear you. Okay, and you three can talk to each other. Okay, maybe you can slide this around a little bit. This, you five here. Oh no, you five here. Yeah, now, y'all are gonna have to talk to each other. Talk softly so the other groups don't hear you. Okay, so you maybe you speak over the okay. All right. And y'all are Can I have let's quickly individualize. You come up and tell me your results, okay? So group one. So why don't you come up and tell me your result? Okay. I don't want y'all to see. Okay. Yeah. Okay. Yeah, I got you. All right. Okay, group one, next person. Next. Next. Quickly. Who's next? Yeah. Okay, next.
Measuring as a group or as individuals?
Did I already got you on? Okay, yes. Next. I was on the other side. You want to type it? Okay. I'll write it down.
Diameter 3.2 area.
Come with me. Okay. Next. Huh? Have y'all gone? Whoever's next.
Are we doing it by group or individual?
Well, we have you?
Yeah.
I did group 2. You were the first in group 3.
We were
us 5.
And that was your whole group's measurement.
Yeah.
I want to individually, like, even though y'all talked, I wanted you to. I wasn't. Yeah, that was the problem, right? So I wasn't clear, and y'all produced one number, right? Even when you talked. Okay. Okay. Well, I mean, let's go with what we've got. Okay, so that was a group. Who?
It was technically the 3 of us, but Kitty gave hers too, so.
Okay, Kitty. Okay, let me have yours then. Okay, so group 2 is good. Group 3 gave me which was group 3? Cole, I think. You were the last one that talked. Okay, and it was representing 5 measurements.
Or I did my measurement and then I did my area, and that's what we
Okay, and but y'all were able to talk, right?
did. Yeah.
Okay.
But we all kind of like concluded around the same, regardless of what you did, because we all have the same ruler. So.
Yeah, that's right. That's right. So that was pretty much the same. So
Pretty much.
yeah. So I will say then it was n equals 5 for that. So that's included. Was that an average?
No.
No. Okay.
I don't think we all averaged it out. I think we just kind of all concluded it was 3.2. Like.
Okay. So it's not average. It's collusion. Okay. Okay. Or I'll say consensus. That sounds less. Consensus. I don't know how to spell it. All right. So group 4. Group 4. Okay. So here we go. What's wrong? Oh, okay. All right. So let me switch this over. Just tab to that. Control 5. Trippy. Okay. So the big reveal. Dun dun dun. Projector's kind of ugly. Golly. I wish I could move the projector. Let me blank it real quick. So this is what I got from all the different reported groups. We have group 1, 3/4. Okay. Yeah, I don't know. Yeah. Were there any units on there at all?
No, that's the whole point.
No units on the ruler at all. Group 2, 3 reported in centimeters, 1 reported in inches, and 1 didn't give a unit. Okay. No indictment. I didn't ask for it. Okay. Group 3, diameter 3.2 area. Right? I just said measure the circle. Right? So what is, area? That's measuring the circle. Yes. 5.48 inches square. So now I've got inches square, but I don't know what that is. I have to figure out, if that's inches or not. And then this was 5 people making the measurement. And when I asked for the individuals, they're like, we didn't take individual measurements. This is, we all agreed on this. So we talked to each other and said, yeah, that's the measurement. So that's not an average. So what do you say there? I said collusion, but I think it's consensus. Yeah, consensus. Yeah, consensus of 5, n equals 5 at least. I was like, we got 5 opinions on that one number, so it's been verified at least. Yeah, so that's consensus. And then group 4, trying to figure out, I got this reporting and it was diameter, but I didn't see a unit on the reports. Yeah, centimeters, but I got what I got, right? So if I send out, measure this, y'all send me back what I get, this is what I get. So number 1 lesson, what do you think is? Let's try to come up with number 1 lesson on this.
Specific.
With the specific, okay, there's an actual word for that. It's called operational definition. Right, you have an operation to do, and I did not give you an operational definition. What does measure mean? So that's your number 1 question. What do you mean by measure? So that's what the ASTM and ISO and all of these standards organizations, that's one of their number 1 jobs, is to have operational definition. So when I say measure a circle, everybody in this field knows what that means. It might be different in petroleum engineering than it is in forensic science, but if this standard is for forensic science, then measure will be defined. And you will know even what units to present it, to produce it, the measurement in, or report the measurement in, and so on. So we've got some things that we can work with here. This was in centimeters, correct? Okay, so we'll say centimeters, and these are in centimeters, with the 1 exception. Okay. Can someone multiply 2.54 by 2? 2.54 by 2.
5.08.
Okay. 5 point what?
5.08.
08. Okay, so I've just converted the 2 inches into centimeters. So now we have our measurements of centimeters. And so let's calculate quickly the standard deviation for each of these. Okay. We have to first calculate the mean, so let's do that. So let me have a few people take this one. So x bar is equal to this, and then we'll do this one here. X bar is equal. Yes.
For this.
And some of you may have the stat functions on your calculator. Let me use them, right? Put in 5.2, hit stat, add, 5.2, 5.19, 5.08, 5.2. Just keep adding those into the stat stack and then hit mean and it tells you the mean. Hit standard deviation, tells you the standard deviation. Practice with that so that you know how to use your calculator. Okay. So who has this first one? 5.2, right? Is there a guard digit? Is there any extra digits?
It's 5.174.
Okay. 5 point what?
174.
4. Okay. I'm keeping these extra digits not because they're significant yet. They're guard digits. So what do I mean by guard digit? Well, since we have multiple measurements, we don't have to use the significant figure convention. We will let the uncertainty tell us where to round. Because again, the reporting principle is all certain digits plus 1 uncertain digit. And so I don't really know where my uncertainty lies here. So I'm going to keep lots of digits until I get my standard deviation. And then I'm going to round. Okay, good. So now, yes. So in order to do this quickly, it's nice to use a table. And so I will have deviations, right, x bar, xi minus x bar. And so I'll just make a column. So you can get 5.2 minus that, 5.2 minus that, 5.19 minus that, 5.08 minus that, and so on. So there's really only 3 different numbers here. So somebody do 5.2 minus this quickly.
0.026.
Okay, 0.26, and that's enough. So this was also here, 0.26, and then down here, 0.026. Someone do the 5.19. I could do it in my head, but when I'm trying to teach, I can't do math in my head. So, yeah. If you've TA'd, you know what I'm talking about. Can't add 2 numbers when you're at the board. Okay.
And then 0 or negative.
Yeah.
0.094.
Negative 0.094.
Squared.
Yeah, exactly. So now then we would square those. Okay, it's tedious, but this is what you got to do. Okay, that's why the stat functions on your calculator are so nice. You don't have to do this whole table thing. So I would encourage you after class to go back to this video, look at this example, and then try to figure out the stat functions so that you can get the same answer. Okay, providing we don't make a mistake. So I'll make squares of these.
The square for the 0.094 is 0.008836.
Okay, 884. Okay. And then someone do another one. Come on, we don't have much time.
1.026 is 8.000676.
That seems okay. Yeah, this one's point on that. All right. Okay, and so then the last one.
For the 0.016, it's 0.000256.
256.
Yes.
Okay. Then add all those together.
Point. 0.011124.
0.11.
124.
Okay. And so that's that sum of the squares of the differences. And then we're going to take that and divide by n minus 1. Okay. So this is 5 measurements. We're going to divide that by 4. Okay. So divide by 4.
0.002781.
0.027.
Yeah, 2781.
Okay, and then we're going to take the square root of that.
.0527.
Okay, so that's our uncertainty. So it's telling us we're uncertain in the hundredths place. And it's not plus or minus 1 in the hundredths place, it's plus or minus 5 in the hundredths place. And so this tells us where we would round our result. So this group could report that x bar is equal to 5.17 and s is equal to 0.05. That would be your reported result. Okay? So you have the mean and the standard deviation. And it's pretty good. Okay? So just looking at this, can you estimate the RSD? Taking this 0.05 and dividing by 5. Okay, this is about 1% of that. If I had 500 over 5, or 5 over 500, that would be 1 on top and 100 on bottom. And so that'd be 1%. That, hopefully you can get to that, where you're just taking the uncertainty, dividing by the mean, and you compare them. And you always just need to look at the sort of 1 digit of uncertainty to do that. This is 5 over 500. Do you see how I'm moving the decimal place on both of them? And it's 5 over 500 or 1 over 100 or 1%. So now this one here, notice how all their numbers are shifted up to 8 because they have a different instrument. But their precision seems very similar. You know, we only see changes in the decimal place, the tenths decimal place in centimeters, and that's really all we saw here too. And so they might have a similar standard deviation. So we might not be able to report a mean for the group because 8.3 is so different than 5, but we might be able to say something about the precision of the group. So the precision of group 2 and the precision of group 4, we might be able to get a pooled standard deviation for that. So has anybody figured out the statistical functions on their calculator? Anybody? You have it? Okay. Can you use your calculator to tell us the mean and standard deviation just to save us some time? So we have 3 8.4s and 1 8.3.
The mean is 8.375. And the standard deviation is 0.05.
Okay, so 0.05 again.
Somebody check me on that though.
Okay. 375. So I end up with 375, but this is telling me where to round. And so instead of 75, I'm going to put 8. Yeah, this was 3.75, but I rounded up because of this. So I want that standard deviation to tell me where to round. Okay. And so this is the reported result for group 4. And you know, if I was looking at that, I was like, ooh, something's wrong. Group 4 says it's 8. The circle is 8, and group 2 says it's 5. We've got a mismatch there. But look at this precision. Everybody can measure with these two instruments to 0.05 centimeters. Oh, I didn't include the units, so this is centimeters. That's bad. A number without a unit is useless, and a result without an estimate of its uncertainty is useless. So, you know, if you ask me what measure the circle, and I say it's 2. 2 what? Right? Well, if I'm measuring in inches, then I'm accurate. I say it's 2, you say it's 5. We're both right because we're both using different units. Okay. So this is, now if we were to do the pooled standard deviation, I was kind of hoping they would be different, but they're exactly the same. So we're going to do the pooled standard deviation, we're going to get 0.05. But let me at least show you how you would calculate the pooled standard deviation. So S pooled equal to the square root, and it's S1. I'm going to use group 2 here. So group 2, S2 squared plus S4 squared. Okay? And I've got a weighted average, so I've got to figure out what numbers to multiply them by. And it's going to be by the degrees of freedom. So this is going to be multiplied by 4, and this is going to be multiplied by 3, and it's going to be divided by 7. Okay, so this number here is in N2, let's do N2, plus N4 minus 2. Okay, so the N for that was 4, and the other one was 5. Add that up, that's 9. 9 minus 2 is 7. That's the total degrees of freedom for both groups. And this was 5 minus 1, or 4. So that was N2. And this is N4 minus 1, or 3. So that was 4 minus 1. See how it's the weighted average of those? You have the sum of all the degrees of freedom here, and then the individual degrees of freedom weighting each of the variances. And so that will give us the result. If we were to put all of these numbers in here, that would be 0.05, and that would be 0.05. And so it's going to be 0.05 in the end. Okay, so 0.05 centimeters. Well, that's great. But that way, if they were different, then we would get a precision that was modified. And since group 2 measured it more times, then they have more weight in terms of the uncertainty than group 4. Makes sense. So that's a great way to take standard deviations for individual data sets and combine them. Now we've got to do something about the different means. And so that would be a huge clue that there's a problem with our measurement instructions, using different instruments, different tools. You all had different tools with your different rulers. Reactions to this. Has this raised anything that you want to point out or ask about? Okay, good. Pretty simple now to think back, to where you saw it the first time or the second time. This is probably the third time or fourth that you've seen it, and hopefully it makes much more sense. Your ability to manipulate data is key. I should say work with data, right? Manipulate sense of mathematical manipulations. Okay. So let's move on to the propagation of uncertainty, the beginning parts of that. So let me cancel out of this one. So we're actually beginning lecture 3 here on propagation of uncertainty. And I just want to go through the density example. It shouldn't take much longer. I mean, we've got about 18 minutes, and that's just plenty. So let's first talk about why do we want to propagate uncertainty. Think about that area measurement, okay? You took the diameter, what is it, the pi r squared, right? So you took the diameter, maybe divided by 2 to get r, and then multiplied by pi. You squared it and then multiplied by pi, and you got the area. Did that change the uncertainty, right? How did that change the uncertainty of the result? It's like you measured diameter, and you computed radius, multiplied by 2 and multiplied by pi. Does the area have the same uncertainty as the radius? Or does the area have the same uncertainty as the diameter? So whenever you manipulate a measured value, you might have the average and standard deviation for your diameter, but what does that mean for the area? And then if you use that in some other calculation, how does that uncertainty propagate through all of those different calculations? And this is an incredibly important skill. So that numerical result without an estimation of its uncertainty is useless. Direct measurements can calculate easily the standard deviation and uncertainty. These were direct measurements, the diameters, and so we just calculated the data and looked at the standard deviation using the equations. But when we do mathematical manipulations, then we need to figure out how those uncertainties combine. So these are the main results of looking at uncertainty analysis. How they came up with these equations is they just took the partial differential equation or partial derivatives of the sums and the products and exponents, and these are the uncertainty equations that come out of that. So notice that these can be simplified. So this, for addition and subtraction, sums and differences, you've got the standard deviation of the result is equal to this equation. Which, if you think about this, what if I squared both sides? I put the square over here, so that would be the variance, or sigma squared for the result. It's just the sum of the variances of all of the addition and subtraction pieces. And so you can summarize it like this. So this equation is very easy to memorize. Is that the variance of the result, if I'm doing addition and subtraction, is just the sum of the variances of all the things I'm adding and subtracting. So the more additions and subtractions I do, the larger my uncertainty becomes, because each one has some uncertainty in it. Now the multiplication and division, see here's the equation. I'm taking y, I'm calculating y by taking a and b, multiplying a times b and dividing by c. And so how do I calculate the uncertainty in y? It depends upon the uncertainties in a, b, and c. And here we have the RSDs, right? That's the uncertainty in A divided by A. So that's the RSD for A. And the next one's the RSD for B. The next one's the RSD for C. And notice they're squared. And so this is a simple equation that's easy to remember. The RSD of the result squared is the sum of the RSDs for all of the things that I'm multiplying and dividing squared. And so you could start with this equation here, and you could take the square root of both sides, and you end up with this. Okay. And if I wanted the uncertainty to get out of RSD, that y value is in the denominator of my RSD. So if I multiply both sides, it comes over to the right, and that's where it shows up. Okay. So prove to yourself. You can start here and get there. And you can put that in your homework pages, right? I started with my RSD equation on the right, and I manipulated it, and voila, I've got the one on the left, okay? Because I think this would be simple to memorize. You can have that in your back pocket mentally, and if you ever need to rederive these equations, you could start there and prove it to yourself. And then you could also the exponents is just a special case of multiplication. It's a times a times a times a, however many x times, right? And so you could take this equation and put in the RSD for a 5 times, and that would be a to the 5th, and you could come up with that. Okay, so let's look at an example here. Let's take a density, which is mass over volume. So this is a simple calculation using 2 measurements. I've gone over essentially these notes in CHEM, so you've probably seen them before, but let's just review. We've made a measurement on a metallic object that weighs 2.503 grams, and it displaces 0.130 milliliters of water. So it's a tiny little object. What's its density, and can you tell if it's gold or tungsten? And I've got the densities for gold and tungsten listed there. So the density calculation is easy. In fact, I think this is a lab, if not here, it was at my last university, of freshman lab. Right? They have different metal blocks, and they put them in water, and they measure the displacement. They calculate the density. So it's freshman calculation on top, okay? Senior calculation on bottom. We're going to do the propagation of uncertainty. So that's pretty straightforward, but I'm going to keep all of those digits temporarily as guard digits, okay? Because it'd be tempting right now to say, I got 19.2538, blah, blah, blah. So it's tungsten. Right, 19.25, my calculator tells me it's tungsten. Okay, but what about the uncertainty? You have uncertainty in both the mass and the volume. So let's calculate the uncertainty, and let's use the propagation of uncertainty equation down there that we just saw in the previous slide. So, it's the uncertainty in that density value is the y value that we just calculated, times the square root of the RSDs of each of those pieces. And so what's the RSD for the mass measurement? It's the uncertainty divided by the measurement. So that's the RSD for mass. And then this is the RSD for volume, 0.05 and 130. Okay, so you see the RSDs in that equation. You square each of them, add them together, take the square root, multiply by 19.2538462. And you end up with 7.6. So that's my uncertainty. So my value that I would report would be, I know the density is 19.3 plus or minus 7.6. And I've seen in both cases, you keep one digit of uncertainty, which could just be 7. So you could say 19 plus or minus 7. But sometimes people report 2. And so I will accept 1 or 2. I won't count that wrong. So I wouldn't count this wrong. In fact, I'm teaching you, to do either one. I like this. I like keeping 2 digits of uncertainty just because it kind of tells you if it's, 7.4 or 7.0 or it was actually 6.6, So I can tell if it's closer to 7 or closer to 8. So this is a problem with answering this second question, is it gold or tungsten? Because we really can't tell. Even though the value came out to be so close to tungsten, we can't say. And the reason is which RSD. So just looking at this, which RSD is giving us a problem? Which is the one that's wrecking our precision? So this is a really good skill to look at those fractions and determine which one's bigger. And you shouldn't need your calculator. You could always do that, but just look at them and see if you can figure it out. Okay. Forget all the decimal places and just look at that. That's a 2 over 25. Okay, so this fraction is 2 over 25, or 1 over 12. What is this one? 5 over 13. That's bigger than 1 over 12. Okay, so this is the one that's wrecking the show. When I say wrecking each other, this is a less precise measurement. So our problem is in the volume measurement, not in the mass. Even though it looks like that's pathetic, doesn't it? I mean, I got a 4-place balance or a 3-place balance, and I've got this mess for a standard deviation. But because it weighs so much, that's not really hurting me. This is what's hurting me. I've got a really tiny volume, and I'm uncertain in the hundredths place. So that's a really important skill, to look at your relative standard deviations of all of your pieces and say, which one is the one that's causing me trouble? And this is just showing it graphically. You know, this is the distribution for the mass. This is the distribution for the volume. You see that curve is wider. That Gaussian curve is wider. And so you take this and square it, and take that and square it, and add them together, take the square root, and you get this overall curve for our density measurement. So this would be if everything was normally distributed, you'd get these Gaussian curves for your measurements. If you measured it an infinite number of times, your data would look like that. And the most common measurement would be in the middle, but then the least common measurements would be out here on the wings, but you'd have this nice smooth curve, and that's what you have. And so this assumption that things are just randomly distributed is a baseline assumption. We're assuming our data is normally distributed with random, volume measurements and mass measurements. And so then we can report a confidence interval based on this normal distribution. So here's our tungsten and gold, and our result is right there in the middle. But if we were to say, what's our 50% confidence interval, it would contain these other elements. So if we wanted to calculate 50% of this area under the curve, if we did sort of an infinite number of measurements, 50% of those measurements would be between these two green lines. And that would include all of these elements. So tantalum, tungsten and gold, rhenium, platinum, osmium, iridium. So it's like a coin toss. It's one of those or it's not. So 50-50, pretty bad confidence interval. And so it might be gold or tungsten. I certainly can't say anything whether it's gold or tungsten. It could be any one of those or not. If I wanted to say 95% confidence, I've got to say, if I want to be confident that I'm 95% confident it's in this list. Okay? Which sounds ridiculous. I mean, look at all the elements that are in there. But you know what's not in there? These. Okay? And if they say the person was poisoned by magnesium, and I measured this, I was like, this wasn't what they were poisoned with. I'm 95% confident this is not magnesium. So even with a crappy instrument and method, I can say something, right? There's less than because it's two-tailed, so there's less than a 2.5% chance that it's magnesium. So it's pretty interesting. Even with a crummy measurement, I can say something. Now, the original question was it tungsten or gold? I'm like, whoa, those are too close together. I can tell you it's not magnesium. But other than that, man, we'll leave it. And so we talked about, but the math worked out. It was 19.25 on my calculator. Okay? But you got to look at the uncertainty. You can't just take that number and run with it. It's tempting. It matched so well, I really think it was tungsten, No, but you've got to look at the uncertainty. Then we will start here with this calibration example and look at how to take the calibration curve. Let me just show you the example we're going to do next. We've got this calibration curve, and then we take 3 more y measurements, and we calculate the x values. Right? You did this all the time in quant and in instrumental. Okay, and we have an uncertainty in y, but rarely do we calculate the uncertainty in x. And so that's propagation of uncertainty, right? I use my y values, 3 y values to tell you what the concentration is, but do I give you a plus or minus on that? Yeah, we can after next time. So that's some foreshadowing. After next time, you'll be able to give a concentration and a plus or minus. Okay, so that's good.